Welcome to the Machine Learning at Home. Today I will speak about outliers. Not just simple outliers, but outliers of groups which were under any dimensional reduction method. So when we apply the dimensional reduction, we will see some shadows of multidimensional clouds. And of course, some marginal dots have probably more importance to us because they might indicate some interesting in-between cases. And it's interesting, of course, to find them, to understand which dots might be marginal or in between. So on the other side, holes, convex holes and ellipses are nice ways to show these different clouds and visualize the differences between them, which includes intersections. So how to find outliers from holes and ellipses? This is an interesting task because these holes and ellipses on a first glance only visualize the information, and many people still think that dimensional reduction is only visualizing method. It's not correct. You can squeeze lots of information from dimensional reductions, and holes and ellipses can help you. So let us start some simple dimensional reduction again. Iris P will be result of PR comp. So principal component analysis of iris data, excluding variable number 5, we will immediately extract components, principal components 1 and 2. And then if we plot it in the most typical way, we colorize different clouds, different species. So we plot it, iris P, and make color equal to the omitted variable number 5, which name is species. Then we received typical 3 species picture: black for setosa, red for versicolor, and green for virginica. Then how to find these outliers? Holes, by definition, must include all points from that particular cloud. So this is a bit contradictory, isn't it? But there is a way. So holes has one option which allow you to skip outliers, so holes will not take them within. So let me show it. First of all, I will create the object iris H because I will need it later. But then I run the same command, holes, uppercase holes, of iris P, result of our principal component analysis, and I need groups equal to species. This variable number 5, iris species. And also important option is outliers equal to false. So I don't need to include them. This is why false. That thing will immediately plot and also keep results inside object iris.h. So it's a double function. Oh, I forgot my package. Now I have it, and I will repeat this command again. Okay, now you can see what's going on. You can see centers with big squares here. You can omit them, but they will be printed by default if you have outliers equal to false. Because outliers, these dots which are outside of holes, are determined by the distance from the center. So what is the method of understanding outliers? A very simple method. It's borrowed from a box plot. Let me show you a very simple example of the box plot. So box plot. So let me plot iris P first dimension, because box plots are univariate technique, against iris species. it will be 3 box plots. 1 box plot of PC1 for first species, 1 box plot for second species, and 1 box plot for third species. Plus I will do some more or less sophisticated colorization. I will use function adjust color. Adjust color. Just color, and we'll make colors semi-transparent. It will look better. So alpha dot f equal to 0.5. Okay, sounds like I made everything, and I will show you box plots. So if you see these box plots, you will see that setosa one has a dot. So this dot regarded as outlier. So a box plot function will calculate which dots are appropriate to call outliers, and exactly the same techniques Hulls will use if you specify outliers equal to false. And only difference, it will use them in 2 dimensions instead of 1 in box plot. So let me show it again. So I'll plot it and then use Hulls. Okay, so these are how these things originated. And we can of course access, that's why we need iris.h. We need to access dots which are determined as outliers. So accession will be done through the attr, through the attributes function. We need to call attribute which name is outliers. And then it will give us numbers. So these are row number 16, row number 42, and row number 107. They are 3 outliers which are clearly visible on this plot, 1, 2, and 3. Interesting. This is a way of taking outlier information even from Hulls. Ellipses are even more naturally distinguishing outliers. So let me show how to work with ellipses. And it's similar, but not exactly the same way. So let us do our plotting again. And then we'll make ellipses here. So instead of Hulls, we'll use ellipses. So we need to change the name of output object. I will call it iris.e. Instead of Hulls, I will type ellipses. And then I will need the same iris.p here, same groups. But outliers is not working for ellipses. I only need to specify centers equal to true to make plots similar to Hulls, for example. Okay. Now you can see some similar picture with centers, but with ellipses, also 95% confident ellipses. By default, they are 95% confidence. So this is our ellipses, and question is now how to find out which exactly dots are outside of each ellipse. This is possible to make, but we need some more function. So we need the object iris.e and function which name is pinhole. That function simply find out which points are within ellipse and which are outside of ellipse. So I will call my output object iris.py, and then we'll apply function pinhole to my iris.p. I still need it, and my iris.e, which contains information about ellipses. So what is iris.pie, iris.py? Let me show it. I will use function tail, which shows you last rows of any object. So it's very simple. For example, the dot number 150 belongs to ellipse setosa? False. Does not belong to ellipse setosa. Is it belong to ellipse versicolor? True. Does it belong to ellipse virginica? Also true. So that dot is within two ellipses. Number 147 is a dot which is only within Virginica, kind of more truthful dot. So now with that very simple false truth data, we can access all information about outliers. For example, how to find which dots are outside of all ellipses. Easy enough. These dots should have false, false, and false. So if it is outside of all ellipses, it should have three falses. If we convert falses to zeros and make a sum of all of them, result will be 0. But if we convert this row, for example, 146, to zeros and ones, sum will be 2, because true will be 1, this true will be 1, false will be 0. Result is 2. And row number 147, after the conversion and summarizing, result will be 1. So we only need to find out how to convert false to 0 and true to 1 and how to summarize results. It's very easy to make in R. So we can apply function which name is apply. Apply to rows. So we can use iris pi. Rows is number 1. We apply sum. And now we calculate which of these sums are equal to 0. And to obtain numbers, we simply use switch function. So this thing will output numbers of dots which are outside of all ellipses. So you see there are quite a big number of dots, so not exactly 1642 107, but interesting is that 16 and 107 are in both of them, 42 by the way not. So this is some intersection between holes and ellipses. We can also try to find untruthful dots, dots which belong to 2 or even 3 ellipses together if possible. Probably not to 3, but to 2 definitely. Some dots will belong to 2 ellipses. So how to make it? Very similar. So we just need to say which sums are not equal to 1, because truthful dot, like 147, will have only one true. And then result of conversion summarizing will be 1. If result is 2, that will be shown as the output of this command. Let us see which dots are non-truthful. So they are either outside of all ellipses, so sum is 0, or they are within 2 ellipses. Sum is 2 or even 3 if possible. Big number of them are outside of all or within 2. Non-truthful dots, I call them. And of course we can use the same technique for holes, but well, we don't need it. I just need to show how that works for holes as well, because that principle is the same thing. So pinhole, iris dot p, iris.h. So iris.h is a hole data, hole without outliers, and we call this new object iris.pih. Okay, and now we can simply find out the same 1642 107 numbers in a different way. At least I hope I will find it. Let us see. So which I will simply repeat it with arrow up, and then instead of PIE, we'll say PIH, and I need equal to 1, to 0, sorry. This is it. Yes, exactly, 16, 42, and 107. That should be. Also, which dots are untruthful in case of holes. So not exactly equal to 1. exclamation mark is not. Okay, some dots are untruthful. For example, 124 likely will be inside 2 holes. So interesting, you can apply many different things to results of this pinhole, point in hole function. This is many different applications, and some of them I will show later. So this was a lesson of how to find outliers, how to squeeze the useful information out of dimensional reduction with the help of ellipses, holes, and pinhole function. Thank you very much.